Good morning, I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the next part of Unit 1, that is related to radio transmitters and receivers. Where we are going to study about different types of antennas that we are going to use for communication purpose. So before that, we are going to study another type of modulation technique, that is vestigial sideband modulation. In short, it is known as VSP. So in case of this vestigial sideband, a vestige or appendage is added to the SSB spectrum. So in case like I have told you in the previous lecture that what is SSB. In case of SSB, either we are transmitting the upper sideband like this one, or we are transmitting the lower sideband. So in the upper sideband and lower sideband, when we are transmitting another part of the band, that is like in case of this, there is USB and this small part will be added. In case of this one, a very small part of USB is added and whole LSB will be transmitted. So that small portion is known as vestige, and its bandwidth, the bandwidth for VSP signal is FM plus FV, that is frequency for the message signal. This is frequency for the small portion, that is known as vestige. So in VSP, vestige is added. So what will be the equation? MVSP omega will be H omega into DSP, which is equivalent to half H omega M omega plus omega C plus M omega omega minus omega C. So these are showing the two sidebands, either it is upper sideband and lower sideband at both the sides, and then it is multiplied by H omega. So this is the VSP modulation from the DSP-SC modulated signal. So this waveform is showing VSP modulation technique. Now next is VSP demodulation. In case of VSP demodulation, the demodulation is done by multiplying the signal with a coherent local carrier and passing it through a low pass filter. So in every kind of demodulation, as you have seen, whether it is SSB-SC, whether it is DSP-SC, or now it is VSP, we have to just multiply the received signal with cosine signal, that is a locally generated carrier signal, like you can see over here. And when you are going to multiply by this, we are getting a higher frequency terms, that is 2 omega C. So this is plus 2 omega C and minus 2 omega C. Then at the receiver side, we have to use a low pass filter. This low pass filter is centered at frequency omega C. Then after passing it through a low pass filter, the higher frequency terms will be filtered out and we are getting the required transmitted signal. So the final demodulated output will be half 1 upon 4 HR omega, H omega plus omega C plus H omega minus omega C multiplied by M omega, where M omega is nothing, it is the message signal. Then if this particular HR omega, H omega plus omega C plus H omega minus omega C is constant over a frequency band of interest, then it is demodulated output is proportional to MT. So this is the VSP demodulated signal. Now the major application of VSP is there in the TV broadcasting or television broadcasting. So here this is transmitter filter response in decibel versus this delta. This is location of the sound carrier, this is location of the picture carrier. A VSP sideband transmission, the transmitter filter response is shown in this figure A, and in this B, that is the relative diode demodulator output, and in C here we are having this receiver filter response. So this is the filter response that we are having, this is the relative diode demodulator output, and here we are having the transmitter filter response. So this is the response that we have transmitted, this is for the received one, and this is how we are having the television broadcasting. The major application is in TV broadcasting. Now next is the quadrature amplitude modulation, that is another important kind of modulation technique, amplitude modulation. So it is similar to the DSP-SC, but it sends two message signals over the same spectrum. So the equation for this particular QAM signal is m1t into cos omega ct. Now m1t is first form of the message signal mt, and this will be m2t, that is another form of message signal, that is m2t, and both are multiplied by first is multiplied by cos omega ct, and when we are taking its 90-degree transformation, after passing through it, we are having this sin omega ct. So next is demodulation uses coherent detection. So mqamt into cos omega ct is equals to m1 cos square theta plus m2 t sin omega ct into cos omega ct. So that will be equivalent to half 1 plus cos omega ct into m1t plus m2t sin 2 omega ct. Then after multiplying this m1t inside the bracket, we are having this equation. Similarly, at the lower hand side, because we are dividing this received signal mt into two path. First is the in phase component, another is the quadrature phase component. Like this is mt signal. Now this will be divided into two arms. First one is in phase component, and this is quadrature component. This is balance modulator, and here we are using a local oscillator which will going to generate cos omega ct, and then it is passed through minus pi by 2, which means we have shifted this cosine signal by 90-degree phase shift. Then we are having this sin omega ct. Now we have to add it together. This will be the addition, and here we are having this particular QAM signal, that is quadrature amplitude modulation. So this will be the message signal. It is passed through balance modulator, and then so this is known as in phase channel. Why this is known as in phase channel? Because the signal input, the signal which is generated over here, that is the cosine signal, that is directly applied to this particular balance modulator, but here we have to phase shift it by 90-degree, which is going to generate sin omega ct, and then we are applying this sin omega ct to this balance modulator. So this is a very simplest form of quadrature amplitude modulation. Now these are the two terms, like first one is mqam multiplied by cos omega ct, and this will be the mqm multiplied by sin omega ct. So this is how these both are then added together. Now next one is the frequency division multiplexing. So multiplexing many baseband signals over a single communication channel. So what is known as multiplexing? Now multiplexing basically is known as when two or more users are using a common channel. Now either they are going to use a common channel on the time division basis or on the frequency division basis. That is the simplest kind of division. So here we are seeing the frequency division method, where let's say there is a band of frequency and it has to be equally divided among n number of users. So here we can see that there are lambda number of users. So first user is applying the message signal, that is m1t, and multiply it by carrier frequency, that is multiplying it by carrier frequency by using a modulator 1. Next is applying m2t and another carrier frequency. So you can see that if there are n number of users, so n carrier frequencies are required to multiply it with the incoming signal. Now these are added together by a summer, and then it is applied to a common communication channel. When it is passed through a communication channel, then there will be different let's say lambda paths are there. So this will be a filter. Then it is passed through a demodulator. So up to this there will be a transmitter, and here from here this will be a receiver. At the receiver there will be an input incoming filter is there, through which the filter is passed. Now let's say it is centered at frequency, carrier frequency corresponding to the frequency. Like first user is using carrier frequency f1, then the first filter is having center frequency f1, f2 up to f lambda. After passing the received signal through these frequencies, these are demodulated. Again, these demodulators are using the same carrier frequency to provide the coherent detection. To provide this coherent detection, this will be used. Then this will be passed through this baseband filter, means a band of filter will be there. Then there will be M1T, M2T up to M lambda T. So this is multiplexing many baseband signals over a single communication channel. So this is the frequency division multiplexing technique. Now next comes the radio transmitter. So after we have seen different types of modulation and demodulation techniques like QAM, DSP, SC, SSP, VSP, we have to now see that how these signals, radio transmitters are there, means how this signal will be transmitted. Actually it is transmitted over a channel. So a simplest block diagram of radio transmitter is, first one is the message signal which will going to generate this signal, that is MT. Now this is passed through this modulator and it is multiplied by a signal, that is carrier signal. I am going to write it, frequency is omega c, or we can write cos 2 pi fct. Then after passing these two signals through modulator, we are having this MT cos omega ct. It is power amplified and radiated through an antenna. So there are two different types of antennas that we can see. Like first type of antenna is omnidirectional antenna. First one is omnidirectional antenna. Now its gain is equals to unity and its radiation pattern is a circle, spherical. Its radiation pattern is spherical, which means it will going to radiate the signal equally in every direction. So that is the main advantage of using the omnidirectional antenna, and mostly we are using it as a reference antenna. Next one is the directive antenna. Now this directive or directional antenna, its radiation pattern is somewhat like this one, where this is the main lobe, major lobe you can say. This is the minor lobe and these are the side lobes. So what is the advantage of using this directive antenna? That most of the energy is radiated in this direction and least energy is radiated in the backward direction, and these energy is of no use. So if you are having in some of the applications you want to direct the energy on only one direction, then you can use this directive antenna. Otherwise this omnidirectional antenna is much more beneficial, but practically it is not possible to use this omnidirectional antenna. It is just used for mathematical calculation because its gain is equivalent to 1 and that will be cancelled out in the mathematical analysis. So that is the case for two types of antennas that we can use. Now radio transmitter second type is, first one block of this particular radio transmitter is impedance matching network. Then there is a driver amplifier, then impedance matching network, again final power amplifier and impedance matching network. So you can see that we have to use an impedance matching network and two types of amplifier, then the signal is passed through this particular antenna. Now this diagram is showing a class C amplifier with tuned output, this one. Next is amplification where alpha is less than 180 degree and this is the output of the tuned section. Now you can see that this is the input voltage that we have applied. This is the threshold voltage. When this crosses this particular threshold value, then this current across the diode will going to appear, and then corresponding to that there will be a output waveform that will be generated across this tuned circuit. Now tuned circuit is nothing, it is a combination of RLC, that is resistance, capacitance and inductance, that is applied used at the output of this class C amplifier. This is nothing, this is the radio frequency coil and this is the VD, that is the drain voltage. This is the input voltage and this will be the drain current. So whenever it crosses a threshold voltage, the drain current will be appear. So this is how the radio transmitter third looks like. Now next is radio transmitter third, that is the second type, radio transmitter third one. In this case, impedance matching network facilitates efficient power coupling. So you can see that this is an impedance matching by L network. Now what is L? L is a combination of two inductance, that is X1 and X2, which is applied or which is connected in an L form, inverted L. R1 is the input resistance, R2 will be the output resistance, that is coupling impedance, that is Z12, this is Z2 output. Then Z2 can be calculated by using this one, that is J R2, means R2 and X2 are connected in parallel. This one R2 and X2 are connected in parallel, so you can calculate this Z2. You have to just multiply. Then after solving this, we are having two terms. First one is the real term, this will be the imaginary term, that is Z2. Then Z12 can be calculated, Z2 plus JX1. So these two are connected in parallel, which we have calculated as Z2, and X1 is connected in series. So we have to just add it together. So these three terms are there, these two terms are these, and JX1 will be added. So for impedance matching, we want R1 should be equals to Z12. So hence equating real and imaginary parts together. So R1 will be R2 X2 square divided by R2 square plus X2 square, and X1 will be is equals to R2 square X2 divided by R2 square plus X2 square. So this is how the impedance matching will equation looks like. So this is the third type of radio transmitter. Next one is fourth type of radio transmitter. So I have told you that two types of antennas are used. So this is the radiation pattern of a directive antenna, where this will be the main lobe, this will be the minor lobe, and these are the side lobes. So in this case, the antenna efficiency formula eta will be given by radiated power divided by input power. Then this will be the directivity, that is d theta phi is equals to radiated power. We have to differentiate the radiated power by with respect to ohm, and this will be the radiated power by 4 pi. Now gain will be g theta phi is equals to d power radiated divided by p in by 4 pi, that is the gain. Now there is an important formula, that is the relation between the directivity and gain of the antenna and efficiency. So that formula is this one, that is G is equals to eta into D. So for 100% efficient system, G will be is equals to D, and that is a very important formula related to the antenna. Now when this is for the directive antenna, let's say we are having this equation for isotropic radiator, or we are having omnidirectional antenna. Omnidirectional antenna and isotropic radiator are same thing. In that case, G will be is equals to 1, so D will be is equals to 1 upon eta. And G is equals to 1, and D will be is equals to 1 upon eta. So that is for the isotropic radiator or for omnidirectional antenna. Both are same thing, that are used for reference purpose only. Now next is radio receivers. So there are different types of receivers. Mainly we are using super heterodyne receiver. So first type of radio receiver is this one, that is receiving system for an amplitude modulated system. That is nothing, it is a super heterodyne receiver only. Now incoming signal is input modulated RF carrier plus the noise. Now what is noise over here? Now in every case, mostly in communication we are using this type of noise, that is AWGN, additive white Gaussian noise. Now why it is known as additive? Because it is additive in nature. As you can see that it can be added. White Gaussian noise because it contains all the frequency components. Gaussian means its spectrum is Gaussian in nature, like you can see, and this is the Gaussian distribution. And when you are going to draw its power spectral density, so from minus infinity to infinity, its power spectral density, that let's say it is SF versus F, its power spectral density is constant, that is n naught by 2. Now n naught is nothing, it is a constant factor that is at time t is equals to 0. So that will be the constant value n naught by 2. So this will be expanded from minus infinity to plus infinity. Now we'll see that what is this radio receiver one looks like. So this is the input modulated waveform. It is first passed through a radio frequency amplifier. So the first block of super heterodyne receiver is a radio frequency amplifier, means an amplifier which will going to amplify at in the frequency range of RF. It is passed through this mixer. Now mixer is another block. It is applied to this local oscillator. Then intermediate frequency amplifier is there, that is IF amplifier. Then this is passed through this modulated IF carrier, that is power is equals to SI plus white noise. So that will be the power spectral density. So you can, I have said that the power spectral density of this particular signal is n naught by 2. You can take it as eta by 2, means eta or n naught is constant divided by 2. So next is the IF amplifier. Now IF amplifier is nothing, it is an intermediate frequency amplifier. Like if you are using it for AM, amplitude modulation, like it is written over here, when you are using it for AM, then IF frequency is 455 kilohertz. If we are using it for FM, then IF frequency will be 10.7 megahertz. That is an important point to note down. For the super heterodyne receiver, when it is used for the amplitude modulation, then IF frequency, constant frequency is 455 kilohertz, and when it is used for frequency modulation, it is 10.7 megahertz. That is standard value in any numerical. If you are having, if the value is not provided to you, then you can use it directly. So what is the main aim of using super heterodyne receiver? Like whatever frequency you are receiving, it will going to centralize, or it will going to convert that incoming frequency to an IF frequency, and its value is 455 in AM case and 10.7 in FM case. Then it will be demodulated. Now demodulator requires a carrier signal for the purpose of demodulation. So that will be generated using this synchronous signal source. It is passed through a baseband filter. At the output of this baseband filter, there is an output baseband signal power that is equivalent to S naught. Then it will be passed through this output will be N naught. So this is a receiving system for an amplitude modulated signal. Now next is the radio receiver second. The advantage of super heterodyne principle is signal strength at receiver antenna is in picowatt range and is best amplified and filtered at intermediate frequency range. The other advantage in multiplexing is to be able to tune to different RF frequency carrier with common processing blocks. Local oscillator frequency need only to be changed. Now next we will move to another part of unit 1, that is need for modulation. We have discussed different types of modulation, but why we basically require modulation. Now, the first advantage of using modulation, it reduces the height of the antenna. So the height of the antenna is a function of wavelength, that is lambda. Now every antenna height is denoted by h. Now h will be lambda by 4. Now lambda by 4, as you can see over here, that height of the antenna is inversely proportional to frequency. So in case of modulation, we are going to increase the frequency of the antenna. When the frequency is increased, it heights the antenna practical height will be reduced, so which has been shown over here. So this is the very important point related to why we require modulation. Next is increase the range of communication, because basically we are converting the low frequency signal to high frequency signal. So the higher signal part can be transmitted through this modulation. It allows multiplexing of the signals, like modulation allows multiplexing of signals, for example, number of TV channels operating simultaneously. So that is the multiplexing is another application. Next is allows adjustment in the bandwidth. It improves the quality of reception. So modulation technique like frequency modulation, pulse code modulation introduces the effect of noise to a great extent. Like in case of digital modulation, since the digital signal is less affected with noise, so whenever we are using the modulation in that particular context, like in digital modulation, then noise will be going to affect the signal less. Next is advantages of amplitude modulation. AM transmitters are less complex as compared to the FM frequency modulators. It uses low bandwidth. AM wave can travel over a longer distance. Its receivers are also simpler, and detection is easy and cost efficient. Next is disadvantages or limitations. So power is wasted in the transmitted signal. AM needs larger bandwidth. AM wave gets affected due to noise. Application of the AM is radio broadcasting and picture transmission in a TV system. So these are the points that we have discussed in today's lecture. Thank you.